All right, we're going to start our plunge into infinite series with just a recap of what we know so far. This is going to just go over the relevant stuff from that very first overview video. I just want to talk about a couple of little things that are going to be relevant for this video. And what most of this video is going to be really about is talking about the geometric series, spending our time figuring out the form of it. It's going to be related to a geometric sequence, and we're going to spend some time trying to figure out if it converges, when it converges, what it converges to, all that kind of stuff. And then at the end, we'll do a couple of examples of telescoping series. So these are going to be our two main types of series for now. And eventually, even as we start understanding more and more about series, we'll find that these are the two types of series that we're going to know best. We're going to know pretty much everything there is to know about these two types of series. So as long as we can recognize them, this will be pretty helpful later on. So let's get going. Just as a quick recap, we're thinking about an infinite series, this infinite number of terms here added up as really a sequence of partial sums. And the partial sums, if you remember, are just the first however many terms of your series added up. So these are finite sums, these partial sums. S sub 1 is the first term only, S sub 2 is the first two terms, S sub 3 is the first three terms. You could notice that the first two terms, if you wanted, you could call this the second partial sum. And so you'll see like S sub 3 is really S sub 2 plus A sub 3. S sub 14 is just the first 14 terms added all up. And so we'll talk about S sub n, the explicit form of the nth partial sum. That's just going to be the first n terms added up, which you can write this way using that summation notation. Since we're talking about this sequence of partial sums, we're going to be caring a lot about the limit of that. So if we can find an explicit formula for the nth partial sum, then hopefully we can see if the limit exists. If it is, if it's equal to some number s, sometimes we call it L for limit, S stands for sum or series here. If that limit equals some number, then that's what our series converges to. And if the limit doesn't exist, then we say the series diverges. So that's where we're at. So our first series, we're going to talk about this geometric series. Now we know this is going to be related to our geometric sequence that looked like this. And so it's not going to be much of a surprise that this is going to be in a similar form. What we're going to do, though, is instead of talking about the series as a whole first, we're first just going to focus on the partial sum. Because remember, we'd like to be able to find convergence of this series. And to do that, so far, our only trick is to take a look at the partial sum, see if we can figure out an explicit form for the nth term of the sequence of partial sums, and then we'll take a limit and see what the limit of that sequence is. So here's our geometric sum. This is a partial sum. You'll notice the indices can be written in a couple of ways. I'll talk about that in a second. This geometric sum is going to have all of the terms still being multiplied by this constant ratio of r, just like our sequence was, but now we're adding them all together. And you'll notice we start with the constant a. You could think of this as ar to the 0 plus ar to the 1 plus ar squared, etc., etc. So that's why we normally will start our index at 0, because we want our first term to just be that coefficient. And because of this, our nth partial sum still needs n number of terms. So because we start counting at 0, we're going to only go up to n minus 1. Now you could write it this way as well. Notice that instead of subtracting 1 in the index, we just put it up in the exponent. But you'll find that most places don't do that. In most places that you look up a geometric series, it's going to have this form, starting at 0, going up to the n minus first term for the partial sum. Oh well, the only qualification that we'll put on here is that a and r are both real numbers, and a is specifically not 0, because if it is, this is a very, very boring series. It's 0 plus 0 plus 0 plus 0 forever and ever and ever. Okay, so this is what our partial sums look like. What we care about is getting the closed form of it, an explicit formula so that we can find a limit. So this is what we're going to do. We're going to take this partial sum, and what I've done here, and this is a pretty common trick, is just multiplied it by r. So instead of just looking at the partial sum, S sub n, the way that we wrote it out first, I'm going to multiply everything by r. So here I've got this r being multiplied, and I just did the distributive property here. And so you'll notice this turns into ar squared, ar cubed, ar to the fourth. And instead of going up to ar to the n minus 1, this is really ar to the n minus 1 times r. And so it's really ar to the n. So that's what we've got there. Actually, I'll leave that. A r to the n minus 1 times r. once we've got that r times s sub n thing set up, what we're going to do is we're going to take this line and we're going to look at a difference here. So I've written that out here. I've got things lined up so that we can hopefully see when that negative gets distributed, we'll have all these minus signs here, and we'll see all the terms kind of lining up with each other. Notice if we combine like terms, those add up to 0, 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 because again, remember, we're subtracting. And so all we're going to be left with is a from the regular partial sum and a minus ar to the n from this r s sub n partial sum thing. So that's what we're left with. I did a little factoring on this. This is really s sub n times, this is really s sub n minus r s sub n, and I just factored out this common factor of s sub n. So this is what we really have here. This weird difference of partial sums with that r factor on it is really just a minus a r to the n. Then you can solve for s sub n by dividing by this little quantity, and this is what we've got. So what we've just done is found an explicit form for this sequence of partial sums. That's going to be really helpful because now we just need to apply a limit to this thing to talk about convergence of our geometric series. So remember, this is the thing that we're interested in. We have a formula for that s sub n. We can take a limit as n goes to infinity on this, and that shouldn't be terribly difficult. So when we talk about the convergence of a geometric series, remember, this is what we're looking at. It's the limit of the partial sum, which we're saying is just this. Now notice this is really going to depend on this term right here. And so I just reminded us, this is the stuff that we talked about before in sequences. We're really talking about this geometric sequence r to the n, and we had 3 options for it. It was either 0 if the absolute value of r was less than 1. So if you had this small value for r, when you raise it to bigger and bigger exponents, it keeps getting smaller and smaller and smaller and goes towards 0. If r was exactly 1, then this sequence goes to 1. And if r was bigger than 1 or less than negative 1, then it either goes off to infinity or it oscillates back and forth up to positive and negative infinity. So either way, it doesn't exist. So what we're going to do is we're going to split this thing into 3 cases based on the value of r, that limit that we're looking at. And we're going to look at the limit in each of these 3 cases, and that should give us a pretty good proof of when the series, the specific geometric series, converges or doesn't. So again, we're trying to figure out what's going on with this. So first, we'll say, let's let r be small. It's between -1 and 1. It could be 0, it could be a half, it could be -1/4, something like that. We're looking at the limit of this partial sum to see if this converges or not, which we already said is this quantity. So let's go ahead and look at that limit. Now what you'll notice is that a is a coefficient that can get factored out. And then we can apply the limit to the numerator and denominator. And then you'll notice that the only part that has an n in it is this little r to the n part. So what I've done is just put the limit here because everything else is staying constant. So this is really the limit that we care about. Now, since r is small, we said by the geometric sequence bit that this goes to 0. So what we're really left with is just a times 1 over 1 minus r, or a over 1 minus r. Now, r is small, so it's never going to be 1, right? Because it can't actually be equal to 1. Since it can't be equal to 1, we don't have to worry about dividing by 0 here. And we'll also notice that a is some coefficient that wasn't 0. So this is a real non-zero number. Some number, we don't really know what it is, but if we knew what a and r were for a specific geometric series, we could just plug it into this. So when our ratio r is small, our series converges, and not only do we know that, we know exactly what it converges to. So that's pretty cool. Let's take a look at the second case when r is exactly equal to 1. Instead of jumping into that big limit, let's just really take a look at what this series is. If r was 1, then the series isn't really a times r to the k. It's a times 1 to the k, but that's just a. So we just have the series of a. A is constant, it's some number, it's non-zero. What that means is that all of the terms look like A, and so our partial sum is just A plus A plus A plus A plus A plus A plus A n times, which is literally defined as n times A. Repeated addition is multiplication. So if our partial sum is just n A's added up, and n is going to infinity, hopefully it's easy for us to see that because A is non-zero, this is going to go to infinity. If you have an infinite number of non-zero things, that's going to go to infinity. Now, I guess we could say, well, maybe it goes to negative infinity, plus or minus infinity, depending on this sign of A. If A is negative, then this is really a whole bunch of subtraction, right? So I probably should have put a little plus or minus in here. Either way, though, we don't care. We know that that limit doesn't exist, which means if that limit of the sequence of partial sums doesn't exist, then the sum diverges. Cool. Last case, we'll call these like big values of R, or really negative values of R, because it could be less than -1. And for this, we'll go back to this limit. We'll go back to this partial sum idea that we've already got. And now when we look at this limit, we know that that is going to not exist. Because R is in this little range here of less than or equal to -1 or bigger than 1, that limit doesn't exist. If this thing doesn't exist, then the whole quantity doesn't exist. So if that whole quantity doesn't exist, then the sum diverges. So 3 cases, and only one of the cases our series converges. So here we go. For a geometric series, as long as A is not 0 and R is a real number, this is our setup. So what does this mean? This means that if I've got something like this, 2 times a quarter to the k, or maybe you'll see this as the sum from k equals 0 up to infinity of 2 over 4 to the k. I could say here, A is equal to 2, and R is equal to 1/4. Since R is small, meaning the absolute value of it is less than 1, I know this converges, and specifically, I know this converges to A over 1 minus a quarter. Oops, I don't want to put A. I want to put 2 over 1 minus a quarter. That's 2 over 3/4. That's 8/3. Bang. So this thing goes to 8/3. So this is a really nice thing. A here is the first term, and R is the constant ratio between terms. My handwriting is extra messy today, but oh well. If our ratio is bigger than 1 or less than -1, if it's a big ratio, we'll just right away say this series diverges. So that's our geometric series. Our second series is telescoping. For this, I think it's probably easiest to just start off with some examples. So I'll kind of describe what's happening here, and I'll describe why we have the name. It's hard to do if I'm not in front of you because it's kind of a visual thing. But anyways, this series, a telescoping series, is one for which when you write out the partial sum, a whole bunch of pairs or collection of terms will add up to 0. So I'm going to say collapse to 0, leaving only certain terms left, and then we get a closed form of a partial sum. So the reason this is called a telescoping series is because you might remember from like old-timey cartoons and old-timey like movies, those little pirate telescopes that look like this, and then you unfold them and they end up looking like this. This is a really, really bad drawing, but oh well. And you'd like put it up to your eye on your boat, you unfold it. I'm doing it with my hands in front of me, but you can't see what I'm talking about. You'd like pull it out and unfold it. This is what we're talking about when we're talking about a telescoping series. So you look through this end and see what's going on over here. Here's your little water and an island and a palm tree. There you go. Land ahoy! Something like that. So for a telescoping series, we're going to be looking for this kind of collapsing terms. And hopefully this next example will illustrate what I'm talking about. So what I want to do is just look at the partial sum of this, S sub n, I'm just going to start writing out terms. It's the first term when k is equal to 1. That's 1 over 2 minus 1 over 2 squared. I'm going to just write exponents on here because I'm going to start eventually running out of stuff that I know. So this is when k was equal to 1. Now when k is equal to 2, I have 1 over 2 squared minus 1 over 2 to the k plus 1. That's 2 cubed. And I'll do another one. When k is equal to 3, I've got 1 over 2 cubed minus 1 over 2 to the 4. And then we've got plus dot, dot, dot. I'll just do like k equals n minus 1. So this is 1 over 2 to the n minus 1. Oops, minus 1 over 2 to the n minus 1 plus 1. So that's just n. And then lastly, I'll do the k equals nth term. 1 over 2 to the n minus 1 over 2 to the n plus 1. And hopefully what you'll notice is these pairs of terms. Right there. And right here. Between our index, k's, we have these pairs that are going to end up matching up, where one of them is negative and one of them is positive. This one is going to match up with the term before it. And so we're going to have all these things match up and add to 0, because one of these things is positive and one is negative. So that's 0, that's 0, that's 0. All the pairs up to these ones are equal to 0. And what we're left with is S sub n equals half minus 1 over 2 to the n plus 1. That's our partial sum. So this is a telescoping series because all these middle pieces collapse down and we're just left with these two kind of ending pieces. You can think of this as like the eye hole that you're looking through, and this is like the lens at the very end that you're looking through. I know that's not actually right, but whatever. Now, this makes it a lot easier for us to actually look at a limit. I'm going to do it in red because it's going to be hard to tell the difference. If we look at a limit as n goes to infinity of this, this is not a hard thing to find a limit of, because I can tell really quickly that this exponent or exponential in the bottom is going to go to infinity. So that whole term is going to go to 0. So this is just a half. So what I've got is that, this thing, oh my gosh, I'm having a hard time writing. Converges to a half. Now, what you're going to find is that sometimes it's difficult to tell if a series is telescoping or not. What you'll start to get used to is looking at things like this. You've got a k and a k plus 1 in the same term. And so you've got this idea of if you put an index in, it's going to actually kind of represent two different values depending on where it goes in. Now, the index doesn't, but you can kind of see how it gets shifted a little bit, and that might match up with a later index. Now, if this was 1 over 2 to the k minus 1 over 2 to the k plus 2, then we might notice that it wouldn't be necessarily adjacent terms that would match up and cancel out. And so sometimes we have to be really careful with writing this out fully and seeing what terms are left over. You'll also notice that the form of this was really important because this last term that we were left with, this 1 over 2 to the n plus 1, that was the part that really impacted whether our limit existed or not. If this wasn't a fraction 1 over 2 to the n plus 1, if it was 2 to the n plus 1, then this last term gets huge. And so if our last term gets really, really, really big as n goes to infinity, then maybe this limit doesn't actually converge. And so our series doesn't converge. So those are some things that you'll have to keep an eye out for. This is one of my favorite types of examples because we might look at this and say, sure, there's a k and a k plus 1 on here, so maybe it's telescoping. But in this first one, we had subtraction. Right? And so that meant that there was one thing with a positive sign and one thing with a negative sign, and that was the stuff that gave us these pairs of terms that added to 0. And here we don't have that. So it can be kind of confusing to see how this is going to work. So what we might want to do is try and take this single fraction with a denominator that has a couple of factors and turn it into two smaller fractions that are maybe added or subtracted together. I'm really smiling on the other side of my microphone here. You can't see me. But maybe you're thinking about what we might use to do that. We can use partial fractions for this. So for something like this, we can use partial fraction decomposition to split this into a sum or maybe hopefully a difference of fractions. And then maybe we have that form that we're kind of hoping for. So what does this look like? Well, this is the series of k equals 1 up to infinity of a over k plus b over k plus 1, right? Is this looking familiar from integration stuff? All right, pause the video. See if you can just figure out the partial fraction stuff first. Get all that squared away, and then see what your fractions look like. And if you want, you can jump into the partial sum if you're feeling relatively confident, but I'll just pick it up assuming you guys have done all the work for the coefficients. If you haven't paused the video, actually do it. I'm serious about it. Pause it. All right, so I went ahead and got a little bit ahead of where I said I was going to, but oh well. So do the partial fractions. Here are your coefficients. I just used that cover-up method. If you want, you could also say, do something like this. A times k plus 1 plus b times k equals 1. And then you could see, looking at the constant terms, that a is equal to 1. And then you could say this is really k plus 1 plus bk equals 1. And so then you could say k plus bk equals 0 by looking at the linear stuff and get negative 1. Either way, just do something in the partial fraction stuff to get those coefficients. So then this is what your series looks like over here. And so then what I've done is I just wrote out the partial sum. So this is my k equals 1 term. This is my k equals 2. I've got a half minus a third. This is my k equals 3. And then I just skipped all the way up to the k equals nth term. And as long as you can justify to yourself and see what the pattern is, then hopefully you can see that this partial sum is really just 1 minus 1 over n plus 1. And so then suddenly the limit of the partial sum is just the limit as n goes to infinity of 1 minus 1 over n plus 1. And hopefully you can see that that term goes to 0, and so this is just 1. So this series that we're looking at that didn't really look telescoping at first converges to 1. Now, here's the power of a telescoping series. If you want, take a couple of minutes, go back, and instead of using partial fraction decomposition to split this thing into that difference of fractions to notice that it was telescoping, go back and just start writing out partial sums. Write out the first 5 or 6 partial sums. Maybe write out a whole bunch of terms with all the k's, the way that it's written here, and see if you can figure out a closed form for the partial sums. You're going to realize that it's not easy to do. It's a difficult thing to find. And that's true in general. Finding the closed form of a partial sum or finding the explicit formula for the sequence of partial sums is normally not easy. We did it for a couple of examples, just by kind of writing things out and looking at them, and you'll do that some more. But getting some tactics like hopefully recognizing this partial fraction split up into a telescoping series, that's going to be a really helpful thing. And eventually we're going to be dealing with series that are complicated enough that we can't just find the closed form version of the partial sum, and we got to do other stuff to even see if our series is going to converge or not, let alone what it's going to converge to. So that's where we're at. That's where we're going. Hopefully this is enough to get you into a bunch of different examples of geometric series and telescoping series and start having some fun with them.